Hello and welcome to this podcast on the law of conservation of energy. Today what we're going to do is we're going to be looking at a very useful topic that is going to show us how energy is converted from one form to another without being created or destroyed. Now, the great part of this is a lot of this is going to be related to something that we should have already studied by now. So what I'm going to do is I'm going to get this introduced with a simple warm-up question. The warm-up question I have for you is this. Can a person survive a 10-story fall into a river? Now, if we think about that for a second, you may have some experience in your life of perhaps jumping off of a high dive, or maybe you've jumped off of a small cliff into a river or a creek, and maybe you've done some of those falls, but 10 stories is a little bit different. And what you may need to be able to do first is you may need to think, well, exactly what is a story? Well, let me give you a little bit more piece of information here. One story is about 10 feet. So that means that the distance I'm asking you here about is a distance of 100 feet. Okay? So that is the target that we're looking at here. But you should know that, well, in physics, we don't really ask you, while feet is a useful thing for a lot of us to think about, we don't usually solve things in terms of feet. So let's go ahead and convert that into meters, which is our usual strategy for these types of problems. So, of course, to convert feet into meters, what we need to do is we need to take that number and divide by 3.28. This is a scale you should be very comfortable with by now, being able to solve for a distance in meters out of a distance in feet. So I'm going to go ahead and round that number to 30.5 meters. So can someone withstand a 30.5 meter fall? Well, to answer that question, you may want to think of this several ways. Probably most of you should be thinking to your kinematics that we've done earlier in the year and be able to think, well, I should know how to solve this, right? And a great question, the way that I would go about solving this is to answer the question, well, how fast would you be going when you hit the water? Well, that's actually something we've solved many times before. If we remember, if we do this problem, where if someone is standing on a cliff and they are up a certain height, but in this case, 30.5 meters, and there is a river down here below, how fast will they be going when they hit the water? Now, kinematics will tell us a way to solve this by saying that the third formula for kinematics is Vf squared equals V naught squared plus 2a delta y. This should be something you're very familiar with and remember, well, we did this problem many times. Now, if you remember what we're saying here, we can work this problem a little bit more and solve for this. What we're really after here is our final velocity. So in order to solve for our final velocity, we first say that our initial velocity is 0, so we're going to take that out, right? And we're going to say that our acceleration is, of course, the acceleration caused by gravity, which we represent by g, and is, of course, a value of 9.8 meters per second squared. Our delta h is our height, or our delta y is our height, h, which in this case is 30.5 meters. So what we're going to do is we're going to rearrange this to say that Vf squared equals 2g times the height. And then if we want to solve for Vf, we of course take the square root of this, 2 times g times h. This is an expression that we solve for many times where we say Vf equals the square root of 2gh. If you want to go ahead and solve for this number to figure out what that comes to, we can do that very easily by crunching some numbers on your calculator. But what I want to do instead is I want to show you how this relates to conservation of energy. Now, alright, so now that we remember a little bit of our kinematics from earlier, what I want to do is I want to take a look at a Hollywood scene where Hollywood does this exact problem in a movie that I really enjoyed called the Bourne Ultimatum. It's a spy movie about this guy who does all these amazing things and has all these special abilities to be able to be this super spy. But at the end of it, he has to jump off a building. And so watch what happens in this clip, and we'll see if we can make some sense of what happens to Jason Bourne. So it's not looking good for our hero. He just fell all the way off the building. He had no choice, but he had to run or be shot. So, could he survive it? Well, we've looked at this from the perspective of kinematics. Now let's take a look at it from the perspective of energy conversion. All right, same problem, same setup, same fall. Now, if we're doing this from the perspective of the conservation of energy, we need to know what energy is it we have to work with. Well, the thing that you should know from your reading in Chapter 6 is that when you are at a height above the ground, you have something called gravitational potential energy. Gravitational potential energy is expressed by saying it is equal to the mass times the gravity times the height, or mgh. This is a very common expression for telling you how much energy you have as you are up in the air. Now, the other type of energy that we have here is as he is falling down, that gravitational energy is changing. It's being converted into something. It's being converted into, of course, kinetic energy. And kinetic energy has a different expression, also found in our reading, that is equal to, that says that it is 1/2 times the mass times the velocity squared. 1/2 mv squared is the kinetic energy. Now, if this is an energy conversion problem, what we are doing then is we are taking our potential energy and we are converting that into our kinetic energy. So what we can do is we set these two expressions equal to one another. This is great. So what we do is we're going to say that our potential energy is becoming our kinetic energy. So let's just bring these two in. We're going to take these two formula and bring them in here and say that mgh equals 1/2 mv squared. So all I did is simply copy those down and bring them in. So the mass of the person falling times gravity times their height equals 1/2 times the mass of the person times their velocity as they fall down. Now, if we do a little bit, some of the first things you should recognize when you see this is, oh, I have two m's, one on each side. So of course you know that we should be able to cancel those m's. So we get rid of those m's and those go away. Now, we're trying to figure out, in the same thing that we did with the first part, how fast is he going when he hit the water? So where we're looking to get out of here is our v. So we need to rearrange. So I'm going to take this 1/2 to the other side. And so I'm going to say we have 2 times g times h equals v squared. And so I'm going to rearrange that to say that the velocity equals the square root of 2gh. Now, I hope you look at that and go, oh, wait a second. That sounds kind of familiar, doesn't it? V equals square root of 2gh? That's exactly what we found up here. Right? See, that's what's wonderful about physics, is this stuff is all connected. It's all related to one another. They don't violate each other by canceling each other out or saying that something isn't true. They support each other. So our kinematics goes along beautifully with our conservation of energy. So this is a great way to reinforce the idea that the kinematics we learned earlier works beautifully with the law of conservation of energy when we're talking about a free-falling object. Alright, so now that we know how this works with conservation of energy and with kinematics, what we're going to do is let's go ahead and plug some numbers in here and see what would really be an answer to our ultimate warm-up question. And if we want to figure out how fast they're going when they hit the water, what we do is we're just going to plug and chug here. So if we say that Vf is the square root of 2 times g times h, let's bring some numbers in here. So this is 2 times 9.8 times 30.5. Of course, we're going to go ahead and just bring in the calculator here and solve for this and say 2 times 9.8 times 30.5 and square root that. And we figure out we get about 24.4. Now, remember, with the units that we're using here, we should be getting a value of 24.4. This was in meters. This is in meters per second squared. So, of course, we're going to be getting an answer in meters per second. Make sure you remember your units on your answer. I'm not worried about your units in your work, but you should have a unit in your answer. Now, 24 meters per second may not mean much to most of us, so we need to convert that into a number that we actually know what that means. Miles per hour is a much more useful conversion. And of course, to convert that into miles per hour, we simply roughly can double that number and a little bit more. You divide by 0.44 will give us that number in miles per hour. So we get about 55.5 miles per hour when he hits the water. Could someone survive a 55 mile per hour hit in the water? Well, that's a good question. And actually the answer to that is it depends on the person. It depends on how you hit the water, whether you hit the water going flat or going in, and whether it depends on a variety of factors. Let's see what happened to our hero Jason Bourne to see if he survived.
Meanwhile, mystery surrounds the fate of David Webb, also known as Jason Bourne, the source behind the exposure of the Blackbriar program. It's been reported that Webb was shot and fell from a Manhattan rooftop into the East River 10 stories below. However, after a 3-day search, Webb's body has yet to be found.
So apparently, it's possible. If it happened in Hollywood, it has to be real, right? Now, that's a great little movie clip to show us a little bit about how we can use math, use physics, and solve the math to figure out what really would be happening to the human body. Now, a better question to look at this, and a more advanced question that I want you to have ready for next time, is this one right here. What you should have ready for next time is how much acceleration did Jason Bourne experience as he fell through the water? That's probably an even better way to assess whether or not it's actually physically possible for a human to do that. That's the thing that I want you to work on next time, and we'll see you again soon.